guess we'll continue what we were talking about last time, and we talked about CNN, and so we'll look into like a bit more like different CNN architecture. So it's kind of a review of like prior works from different research group here. So we mentioned AlexNet, like this is the oldest one, not the oldest one. I mean the kind of the earliest one, like using CNN. Of course, like that one like before that, Roulette 5 in the 90s. So AlexNet is more or less similar to Roulette 5, and we mentioned that there's some interesting structure there. That's kind of artificial because like at that time it's kind of a historical node that they train the model using like kind of old GPU GTX 580s only have 3 gigabytes of memory, so they are forced to split their model into 2 parts. And there's some parts that they kind of like have the lateral kind of like they split the lateral completely. That for example for the conflict here, the two lateral on the 2 GPUs are not communicate to each other, but there's some other components they kind of like talk to each other. So and that's AlexNet we talked about last time, and it is the winner for the ImageNet challenge in like 2012. And then like we kind of talk about CFLET very briefly. It's more or less very similar to AlexNet. The only difference is like they kind of like trick some of the parameters here and there, and they managed to reduce the error rate from like 18% to like 11%. And so then like we kind of, I guess we also went for VGGNet, not I guess also kind of briefly I would say. So for VGGNet, like the authors kind of like try different configurations, and then eventually they find okay, this configuration is the best. And actually some of the trick they use, of course at the beginning they may not realize that, but after trying different combinations they realize that like they have certain gains like using like smaller filters, let's say, compared with like larger filters. For example, like in earlier networks, it's common to use like larger filters like 7x7. But if you think of that, like if you have like 3x3 filters, and if you like stack that for like 3x3 conf filters like for like let's say 3 times, then you have the same effect of like a 7x7 filters, right? More or less. And also like that you in each layer you introduce some nonlinearity also, because it goes through a value layer or like value layer there. And so therefore like and moreover actually you get extra gain because I compare with like a 7x7 layers conf layer. For there like you have like 7 square C square, like so many parameters per channel, right? But instead if you have like 3x3 filters there, then you will only have like 3 square C square and multiplied by 3 layers, so many parameters. So you always also have like less number of parameters. So it kind of like you will be less like, so because you have less number of parameters, therefore you also need less amount of like data to train your model. So I guess we showed this last time. We didn't go for everything because you can read this. I also recommend that you guys, when you play with actual networks, you also try to go for this kind of exercise just to see like each layer, how many parameters are actually there, and also like how much memory are needed like for running this network for each layer. So therefore like it will be easier for you to debug. You realize like, for example, if you're out of memory, you know like which layer actually causing you the problem. And if you go down this list, for example, you see like fully connected layer actually have many variables. For example, it have like 100k of variables. just for the last the third last like fully connected layer. And the total number of variables for VGGNet is about like 138 kind of million variables. Sorry, I said 100K, I mean 100 million. So that out of this 138 million, just this layer is already 100 million. So that's something is not so preferable. In practice, actually, later works have suggested some solution for that. Actually, for later work, they instead of using fully connected layer, people tend to use like average pooling. We will mention this later on, actually. For example, okay, this is still like VGGNet, and for the same year, VGGNet didn't win the first place for the competition. It win like, okay, for the ImageNet competition, there's like several different categories. I think like it won one or two categories, but most of this is won by the GoogleNet. And the GoogleNet, okay, actually last time I guess we ended like somewhere here, like we didn't talk about GoogleNet. So as the name suggests, it's by Google, and the main idea is that they introduce some kind of this inception module. So it actually borrows some idea from a paper called Network in Network. There's a paper by it's also a well-cited paper by NUS, the National University of Singapore. And so one of the ideas is like in the network, you just look at like you pull into like you have a kind of like network module here, like something like that. So your whole network is composed of like a number of like network module, and that paper also have some nice idea. For example, like as I mentioned, like instead of using fully connected layer, that paper also suggested to use average pooling, such that we can avoid less. I mean, we can reduce the number of parameters and avoid overfitting. So let's back to GoogleNet here. So as I suggested, like he borrowed lots of ideas from that network in network paper. So they also avoid using like fully connected layer in the last several layers, and and they use certain tricks I will mention later on. So they can manage to reduce a large number of parameters. So if you look at the VGGNet, it has like 100 something millions of parameters, but here they only have 5 million of parameters. And as I mentioned, they won the ImageNet competition for a lot of categories, and in particular, they won the like classification category. And so let's go more. Yes.
The inception model is 2-layer or 3-layer or just 1 layer?
Inception module actually has a couple layers. You can see like actually 2 layers. Here is like actually you can think of it as like 2 layers here. Yeah. So but the original idea is more or less like this. The original idea is like, okay, instead of just trying to pick just one particular size of filter, let's try to use combinations of filters of different sizes. So let's say I can go for like 1x1 convolution layers and 3x3, 5x5, and so on. And we can also have like let's say a 3x3 mask pooling. I know that like for the mask pooling here, the stripe is 1, so it doesn't do any downsampling. So what and also like for 3x3 and 5x5, they do the padding such that the size of the output after each of these conv layer will be the same. So therefore they will just pad so they have some output from here and some output from here and some output from here, and they simply stack this output together, so they form like 4 stacks like that. So and the problem here is like we have like lots of parameters, and also like the capacity is pretty high, and basically maybe you can count a little bit. Let's say it have like the 1x1 is like 128 of a depth of 128. I guess it's like a review of last time here. So okay, given the setting here, what's the depth of the output here? Can you count like what's the depth of the output here? So we have 128. So basically we have 128 from here, right? And we have like, and by the way, what's the size of the filter here? Do you still remember like size of the filter? It's 1 by 1, but 1 by 1. Well, I mean, remember that like conv-let, unlike in signal processing, conv-let here is always like kind of volumetric. So you have the filter is like volumetric. So the size of the filter here is actually 1 by 1 by 256 because the depth of the input here is 256. So then like the output depth here like is 128, right? That's 192, 96 here. So if you combine them all together, so stack them all together, so you should have the output of the size like this, right? And for mass pooling, like here we do not have any downsampling effect here, so therefore like still have 256 here. So you get like total like the depth from like 256 goes up to like 672. So and there's a lot of operation also besides like your output just expand a lot. The number of operations you may count that. I probably not going to, okay, yeah, I can go for a little bit of that. So if you just count the number of operations, let's say going for here, so the filter size is like 1 by 1 by 256, right? And you need to go through the space like 28 by 28, and then you have 128 so many filters there, so you need to, so the total number of like operation will be just the product of all this. So just for this part here, and for this part similarly, we have like 28 by 28 by 192 by 3 by 3 by 256. So if you add all this together, it's like 54 million operations. So it's pretty huge. So how do we tackle that? Do you remember like we learned some trick last time that for kind of to reduce the number of operations, like we mentioned one trick last time actually, but maybe yeah, I guess we didn't go through that like so in so much detail, but the trick here is basically you use the 1 by 1 convolution filter, so as a way to compress your inputs. So instead of, so it's like this example again, like if you have the inputs like this, if you go for a 1 by 1 conv filter, let's say with a filter length, a stack of filter with like 32 different filters, then essentially you will compress the original input with depth like 64 to 32. So doing that, like you can basically like first, like let's say you can first compress your input before going through this conv layer. Let's say you can compress the input like 3 by 3 conv layer with this 1 by 1 filters, and also do the same thing for 5 by 5 also. And you can also like after doing the mass pooling, also like do a 1 by 1 to further compress your output. So by doing this, then you can reduce the output size from like originally, I think it's like I forgot the number now. It's like 529 so many no, that's the operation, from depth of 672 like compressed to let's say like 480, something like that. And you can also reduce the number of operations like by quite a bit by just doing something like this. So it's very simple idea basically, and as I mentioned, like the GoogleNet is just packed like lots of this so-called inception module like multiple times, and so it's kind of like this. And here like they also like at the intermediate level, they also pull out some of the the intermediate output and attach to the some conf layer and also fully connected layer. Okay, they didn't use fully connected layer as I mentioned. They just use some average pooling. So the idea is like they can get some intermediate output and you can train also here. So you can for example, this is an end-to-end classification problem. So you can also compute the loss like for at here and also at here. So you have a multiple loss here. So this can help you to essentially train the earlier layers. So have kind of like you expect like you compute just again like train end-to-end, but because you have these layers here, so this kind of help you to train just these several layers, and this help you to train like these layers and so on. Like, so any questions here? So it's more or less the GoogleNet architecture. And yeah, this is like the full architecture here. Actually just repeating what I said, like they have this auxiliary output like at the intermediate layer, so to help you to kind of like for faster convergence for training. And they do not have this they remove the fully connected layer. Instead they do a average pooling. So for average pooling, like what they did is basically for example, like in the last layer, let's say you have a output, let's say you have a depth, maybe it's conf layer, maybe you have eventually something like the output like 24 by 24. Okay, this number is just arbitrary. I just, let's say, and by 1,000, let's say the depth is 1,000 here, let's say. So what they mean by average pooling is like, so they will just for each filter, they will just take the average across each plane here. So therefore, like the output will be just simply a vector of 1,000, a length of 1,000. And then you can take this output here. For example, if you do a 1,000 classes classification, you can just take this output immediately, plug into a softmax layer, and you can use this for classification. So instead of like doing the fully connected layer. So, and this is some summary of the GoogleNet. So it has like 22 layers, and it have this kind of inception module, and it has no fully connected layers. And it turns out it can have much less parameters than AlexNet. It reduced the number of parameters by 12 times. And yeah, it has a pretty good performance. And finally, I'm not sure it's finally, but I'd like to talk about WestLab. So WestLab is by Microsoft. It's MSRA, Microsoft Research Asia. And so as you can see, like this chart gives you the accuracy. Sorry, it's not accuracy, really the testing error for the classification challenge. And in terms of the number of layers of the network also. So you can say for before 2012, we have like shallow network, just 2 layers. And afterwards, you have AlexNet and CFNet, like have 8 layers. And then like next you go to like 19 and 20 something. And then in 2015, you go all the way to 152, like many layers really. So, and I think like this is also like, batch normalization is introduced. I don't remember exactly, maybe time, I need to double check. But actually, batch normalization that we mentioned earlier, has a lot to do with like the possibilities to stack so many layers. Without batch normalization, it's actually very difficult to go like really beyond 20 layers. Train between you just cannot get it converged basically. And WestLab, why it's called WestLab is actually is referring to residual network. So the idea is basically, so you think of like if I have like larger and larger network, it's actually getting pretty difficult to train this larger network. So some of the earlier idea, what people think of is like, okay, maybe we can first train the earlier layers. So just assume that we have some earlier layers and we train it. Then afterward, then we train more layers and think of these other layers as refinement. So since it's refinement, then we can think of, okay, there's output here already. So for example, I train end-to-end and want to do classification, and this already have some nice feature for the classification. I call it X here. And then I add some refinement layer, and this refinement layer is just going to train instead of like getting the train the output fx train the output some, I don't have a label here. Train the output, let's say ox directly. So instead, I just want to train a residual in the sense that ox will be just equal to this residual fx plus x here, the input x here. So therefore, in the sense that, okay, what's the difference from the original, you will say. So the main difference, if you think of that, if I'm really training just this residual here, then if I'm already doing a very good job here, then the weight here, you expect the residual here should be very small, right? So therefore, like the weight here will be more or less 0, right? So I would expect like this fx is more or less 0. So this weight here you can assume that it start with is already should be more or less 0. So you don't need to change tiny things like variations such that this WESTlet will work well. So another way to interpret why WESTlet is doing better, because like as you train it this way, you see that like you have a network that have some high I would say like some information highway that bypass some of the layer here. So if you remember how we do backpop, that if we have like a computation unit here, is like just an addition here. When you do the backpop, you will just like pass gradient to this. Just distribute the gradient on this link here and also this link here. So we just forward gradient directly. Bypass these two layers here. So therefore, like it's easier, like because you have all this super highway here, you are getting easier to bypass. You have like gradients to backpop all the way to the earlier layers. So that's usually why people think that why WESTlet is doing so much better than earlier model. Actually, it's doing so well that like in 2015 it just won basically all the competitions. So it won the ImageNet competition, basically all the categories, and also like the Kuko competition, also similar competition, also like won basically all categories. This is just another inspiration, like why they doing this is also like they did some experiment that like you just stack more layers. So because as we mentioned earlier, right, if you have any machine learning models, supposedly like you can always able to overfit your model, right? If you have a small training set, then it's reasonable that like you can if you have more complex model, then your training error should always go down, right? So therefore, like if you go from like 20 layers to 56 layers, supposedly for the other layers you can do nothing, right? Because if you have 20 layers, supposedly, and you have the additional 36 layer, this 36 layer, it can be, say, if you really can train it well, it can be just some identity layers here, right? So therefore, like, there's no reason that like you cannot have a increased capacity, from 20 layers to 56 layer, and you don't have like training errors that actually go down. But instead, like what they found in the paper is that like if in general at that time if they increase the number of layers, then not just the testing error is getting worse, but also the training error is getting worse. So therefore, like definitely this is some training issue. It's not related to overfittings or something like that. So therefore, that's one of the rationale for them like to introduce this Westlet there. And so this is more or less the same thing. I think I already talk about this actually. So that's basically this is the original network you can think of. If I stack more layers, it would be just like this. So instead for the Westlet, they basically have something like this. They bypass several layers. So therefore, essentially instead like they're training this guy is actually the difference of the output of with the input. And so that's still the Westlet. So this is more or less the lateral here. Okay, so they use all the way just 3x3 complex. At the beginning, they have a 7x7 complex to begin with, but afterward they all use like small filters, and they also like downsample. They use strike 2 to downsample it. So they do not do much polling. Basically, like they just like for example here like they have 3x3 like 64 each of that have 64 filters, and they decrease the size in the next group here by basically in the first layer they just do a stripe 2 like conf layer conf filter, and then afterward they just keep stripe 1. So they therefore like they here I don't know exactly the size for that, but let's say if the size here is 36, so then after this stripe 2 here they go down to 18 and they keep 18 here, and then like in the next group they go down further, something like have the size like smaller and smaller. So I mean this is 36 by 36, let's say 18 by 18. And and they don't have like a bunch of fully connected layers, but they keep one fully connected layer. So unlike the GoogleNet there, they use average polling. So they have average polling to get down to here like 5, 12, so many. It's basically after this average polling here it just get to a vector of like length 5, 12. Then it have one fully connected layer with output like 1,000, because like 1,000 classes. Then this is a fully connected layer, so it's just training a fully connected layer here. And then like again like after that it just go for a softmax. And and they have different variations here. They try like different depths like 34, like 50, 101, 152 is the longest one. And also for the longer, I mean the deeper network, they also use the bottleneck layer. So basically it's just like you use the 1x1 filters to compress the input. So so basically they use 1x1 filter like this. So they first compress the input like to depth 64, and then they use a 3x3 conf of like 64, but then they extend this again, like expand this back to a depth like 256 at the output. So any questions? So it's all pretty simple. So a little bit detail for training, they use half-year like initialization and batch normalization, and remember like okay, we mentioned this like weight initialization trick, right? This is also that was introduced in this paper also. And they use SGD with momentum, and the learning weight is pretty standard. They use a fixed learning weight like 0.1, and then like they can reduce the learning weight whenever it went to a pad 2, like for the training error. The mini batch size like 256. They have weight decay like it's 10 to minus 5, and no dropout was used. So in the paper they said like no dropout is necessary. But I don't know like whether like you can gain or not. Maybe there's some other paper afterward, but I don't quite remember whether like whether the people actually get a better result using dropout. So and this is like some result they for classification they get really good result, like I think it's 3.5 something, like for accuracy and detection, and they and this is like detection localization or something. This is kind of crazy if you see that. Like it's not the result. This is like saying like how much better than the second best. So it's like 16% is better than the second best, and like localization is 27% better than the second best, and so on. And 3.6%, as I mentioned, is actually better than human performance. Of course, that is human performance of one human. That's Andre Karpathy. So if you have an ensemble of human, maybe you can gain more. But I don't think people have data set for that. So there's just like what is my time? So there's some nice paper. There's a nice paper, recent paper, for comparison of like different networks models. So as you can see, like okay, they compare with like AlexNet, VGGNet, and so on, like WestNet, and this is really helpful. I think like this is like the number of operations. So this is like the computational capacity, and this is the accuracy. And the size of this circle here is like the memory usage of the network. So you can see like for VGGNet, it uses up lots of memory and also like lots of computations. In terms of accuracy, it's doing okay, but it's not the best. So probably GoogleNet is like very efficient, like it's using like very little amount of like computation, and also like in terms of like memory also. So if in terms of like pure performance, like you have like WestNet is here, and there's also Inception Nets like by Google, like it's basically different versions. It's basically like they use the Inception module idea and combine with WestNet, and that get like very high performance. And there's more curves that you can find from the paper. I guess you can just dig it up yourself. Like there's also power consumption, and like how much time you spend for a pass. That probably very useful when you implement like actual something like probably for industrial project. Like will be really you don't want to like have your application just use up like 90% of the cell phone power or something like that. So yeah, I guess I would mention some a few other architectures also, or like go for a couple like other papers. Just briefly mention them. One of them I already mentioned is the Laboratory Network paper. There's a pretty well cited paper. I think it has 1,000 citations, and it mentioned it inspired basically like both GoogleNet and like WestNet, and also like they kind of introduced this the idea of using average polling instead of like fully connected layer, and I think it's like worth like kind of like flipping through. And there's also some newer paper beyond WestNet, for example, like by the same group. They just like they have, for example, this work, they found that like instead of doing the setup as what they did in the earlier paper, they find that if they have like stacking like this way, they get better result. And also like people also look into, let's say, some of the trade-off between depth and width. So people find that like now it's no longer like always deeper is better. Of course, like deeper is you can gain, but sometimes you can trade it off if you have a wider network. For example, in this paper, it say, okay, if I just make it wider in the sense is like here, the depth of the conf left for this layer, let's say it's just f. If you make it f by k here, then essentially it's like a wider residual block here, and then like you actually can reduce the number of layers and still can outperform the original Westlet. So now you only have like 50 layers instead of like 152 layers. So very similar idea is also like proposed by the same authors like of the Westlet. They call it Westlets here. So instead of like going completely f-depth here, I mean like just like you pad like more conf layer there. So they just put one more structure there. So they try they have like these individual paths they call them like cardinality somehow, and they find that like they can gain a bit more like doing that. And and there also one paper I guess we mentioned earlier that's that actually when we talk about like drop out and other like regularization, that basically they just when doing training they randomly bypass some of the layer. They basically just say they assume okay the layer is not there, and testing they just use all the layers and they find that like they can improve the performance somehow. And there's also like other work like a very recent, they call it FactoNet. So again, like, it's pretty similar idea. Now they have each block. It is a little bit like the inception layer, but now they have like this fractal structure here. Just you can see like it just continue to expand, and they also find that it's somehow they argue that it can get better performance. And there's also like some other paper trying to extend this kind of information highway, that kind of idea, just have like better gradient propagation by introducing lots of kind of links to bypass like intermediate layers. So and the small filter idea is also like mentioned a lot, like and there's a kind of a line of works is basically trying to squeeze the lateral. Actually, there's lots of practical values here. Again, like AlexLat and all these other lateral is like pretty big, and potentially like for example, this paper here, they claim that you can reduce the number of parameters by 50 times and still can keep like similar performance. So some of the trick that we already mentioned is using small filters just to squeeze your input a little bit. To use the 1x1 filters, this bottleneck filter there, and other is they do some quantization just to compress the parameter somehow. So I didn't really go through the paper. You need to go into the detail if you're interested. But apparently there's lots of practical values for works like this. So and this is a summary of what we talk about kind of today, just some of these architectures here. And so we went for like AlexLat again, I guess, like VGG and like GoogleNet, Westlet, and also some of these other architectures that we just briefly went through that. So any questions? I guess like all of you guys looks pretty tired. Let's see. I have half an hour here. So I have some slides actually. I have that is like for last semester, not last year. So I'm thinking whether I want to go through that. Actually, maybe you can just go through it yourself. It's more or less like just repeating what we already went through. For example, like data augmentation, there's some of the CNN trick we can go through, like use data augmentation to take advantage of that. Like if you don't have enough data, just be creative and generate more data. And use of small filter, we already mentioned that. Implementing CNN, we didn't mention that, but I'll see like if we want to go through that. GPUs apparently it's getting more and more popular to use GPUs, and actually besides that, like there's also like tensor processing unit by Google that claim to have like even better for training neural network. So we may talk about that later time. So I guess data augmentation. This is we already go through that like earlier, so I won't talk about that anymore. So but maybe I just say a couple words about like transfer learning. So all these models you see like WestNet, like VGGNet, like GoogleNet, and so on. They are all available like in the Cafe Zoo. Like they have a model zoo there. Like you can pull like all this lateral out, and they all can also like port to other framework. I believe like for example like from Torch to Torch or something like else, and using those network as a starting point. For example, if you have another problem, let's say, you can fix some of the parameters, right? For example, you start with like a simple AlexNet. Let's say, I'm not sure this is an AlexNet. Maybe this, yeah. And then like, you can, let's say this is the input here, and you can fix the earlier layers and only train the last layer, let's say. For example, like you have a different classification problem. Instead of like you have 1,000 classes, you only have like 100 classes. So here maybe you don't need this. The last layer here, like instead of have fully connected like 1,000 with 1,000 outputs here, so you can change it to like just with 100 outputs here. So and then you can just have something right away. At least like it probably not the best, but it will be something like you can use immediately. So and if you have more data, then you can do some fine tuning. Let's say freeze the earlier layers and then like train even like the earlier layers there. I mean the later layers here. So this is like something very useful. So that's just a paper mentioned about that. And so that's some idea here, like that's what already mentioned, like in the earlier slide. So if you have a very similar data set and you have very little of data, then you can just like do some, basically the last layer, you can just, as I mentioned, you can add a different like fully connected layer, or you can do some average polling, and you can even do a linear classification, SVM and so on. And to have a classifier just custom for your data set. And if you have like a little bit more data, then you can fine tune a little bit more layers, as I mentioned. So, but if you have like very different data sets, then you probably need to fine tune more layers. And hopefully you will have more data for that. And if you have a very different data set, for example, you are doing medical data, apparently it will be quite different from what you see for lateral images. Then you may get into a little bit trouble. Then you probably want to find some more data for you to do training. Anyway, just there's just some takeaway there. Like so, people said that like if your deep learning does not work for if you only have little data, but to use transfer learning, actually, as long as you have some pre-trained model, actually you can still use deep learning to achieve like reasonably well. and check out the model zoo like from Cafe and also Cafe 2. They have all these like models there. So I guess like I probably stop here because I want